Hello everybody, my name is Hirar Sinan Uda. I am based in manufacturing engineering. Today we are going to represent our work which is about conception of a human machine interface for supervision of the FIS2 MPS system via WinSysFixi. As a forward, I choose to talk about Industry 4.0 because in recent years, the media has been talking a lot about the transformation called Industry 4.0. Yet many company owners don't really know what it is all about. Beyond the concept itself, you need to know that the transition to Industry 4.0 will popularize your productivity considerably, reduce your costs, and greatly improve quality. What is Industry 4.0? Industry 4.0, or in other words, the fourth industrial revolution, defined by the advancement of new technologies, the evolution and transformation of industry and production system. What is Industry 4.0 all about? In general terms, this evolution granulates the rapid operation of machine while at the same time coping with production slowdowns during certain period of activity. What is more, the intelligence involved guarantees the reliability of use and prevent numerous anomalies. For the work plan, we will start with an introduction, then we will define what SCADA is, the component, the basic function of SCADA, the different means of communication. Then we will give a brief overview of the state of the art on SCADA systems, the work objective, the work carried out. Finally, we have an interpretation of the result and conclusion. Introduction. The industrial environment considers industrial safety to be a very important part of ensuring integrity in the control of industrial systems, such that industrial equipment cannot be implemented without any evidence to ensure the desired operation. Consequently, safety not only prevents malfunction causing material and human damage, but also guarantees a continuation and stability of production, as well as ensuring the survival of the industrial plant. Today, another challenge is being taken up with regard to the automation of process supervision using intelligent SCADA system in the form of a human-machine interface that offer industry the possibility of intervening on automated system remotely. SCADA is defined as a set of equipment that provide a remote operator with sufficient information to determine the status of a particular piece of equipment or process and the cause action to be taken regarding that equipment or process without being physically present. The basic function of SCADA includes supervision. Is the function that provides the operator with an immediate view of the evolution of the process over time by analyzing the sequence of operating states. To be effective, the human-machine interface must provide the operator with a rapid and complete picture of the entire process, highlighting the state of evolution and unaccepting deviation. Control function of a SCADA system consists in the ability of the control system to interact with the controller process in order to modify its evolution according to pre-established rules of decision taken by the operator. The task of data acquisition is to ensure error-free transfer of information between the process and supervision in the context characterized by a variety of transmission media and different communication protocols. In order to enrich our work, we have drawn on several works by researchers in the field of supervision. In this section, we will present some of works in which we have the work of Mr. Khoznatov and Valyov on the oil and gas fields, which uses the SCADA systems in order to guarantee the control and the monitoring of production processes. Also, we have the work of Mr. Bernard on Industry 4.0, which uses SCADA system to ensure the proper functioning of this complex system. Also, there are other works on the pumping treatment plants, which have used the SCADA systems in order to facilitate the task of control command and to improve the quality of optimizing the distribution of this primordial resource. On purpose of this work, from the state of the art, we conclude that the principle of supervision application is almost the same. What is different is the means used and the domain, but the goal remains the same. So, what is interesting is how to give the best presentation of human-machine interface with the minimum variables, also with a professional touch and present simplicity in human-machine interface design at the same time. So, our contribution consists in modeling, studying, and developing a supervisory human-machine interface, trying to simplify human-machine interface design and give the best presentation, trying to create a more professional supervisory human-machine interface. So our goal is the development and design of on human-machine interface for supervision and control of the MPS 500 system, which is a complete automated production system containing several types of sensors, actuators, PLC, cables, and industrial networks, using both Siemens PLC simulated from the Step 7 Semantic Manager suite and WinCC runtime. The modular production system, flexible manufacturing system 500 is automated system, and the number 500 means the current layout around the conveyor. This system is currently installed in our research laboratory at the University of Tlemcen. This system is composed of 6 stations plus a main conveyor that can manage the circulation of the production flow between these stations using the well-oriented pallets. The system is equipped with Siemens programmable industrial controller by Step 7 software and an industrial brain dedicated to Mitsubishi robot in the assembly station. The means of communication between the different stations and the controllers are via Profibus cables, Syslane cables, and IZ cables, can open cables. The first station is composed of 2 stations. The store station guarantees the availability of all the parts and the store level and transfer them to the next station, which is the control station by the rotating turner. The production station is used to process parts under 2 machines, the control armature and the drill. The assembly station is used to assemble parts using a 6 Cartesian robot. access intended for storing and removing parts. The delivery station is used to sort parts according to color. Here is a human-machine interface developed from the distribution station, where we used real components like the conveyor sensors that exist in the WinCC library. We also modeled and draw other equipment using sample objects, for example the rotating turner pallet. We also use the animation principle: all that is in red when stops and all that is in green while running. Figure 1 shows the human-machine interface of the FIS2MPS 500 dispensing control station in stop mode. Note the rotary screwdriver in front of the control station and the cylinder at the bottom. Figure 2 shows the human-machine interface of the FIS2MPS 500 dispense control station in reset mode to initialize the station. Figure 1, it shows that the start button is on and the stop and the reset button is off. Now that the magazine is full, the rotating spindle is in front of the magazine. Figure 2 shows the human-machine interface of the distribution control station in runtime mode, the start button. Now that the rotating spindle sacking the parts and pivoting toward the control station. This figure shows the human-machine interface of the dispense control station in RAM mode. When the start button is pressed, in this figure, it can be seen that the magazine contains parts. Also, the rotary turner in front of the magazine and the parts at pallet level. This is the machining station interface, where we use real components such as optical proximity sensors, electromechanical sensors, capacitive sensors, rotary table, parts, and electric motors. We also use simple objects to model the control armature and the rotary table. The figure 1 shows the station in reset mode. The control armature and the drill are the top in the initial position, and the dial table is stopped. Also, we notice the absence of the parts at the dial table. Figure 2 shows the station in operating mode. When the sensor detects the presence of the parts at the dial table, the latter turns 60 degrees in order to put the parts at the level of the control armature. Figure 1 shows the station in operating mode. Note that the control armature at the bottom to control the holes of the parts. Figure 2 shows the station in operating mode. The dial table rotates 60 degrees to push the parts on to drill level. This figure shows the human-machine interface of the FIS2MPS 500 system machining station in stop mode. Now that all actuators are in their initial position. Here is the human-machine interface of the manipulator station, where we use the simple objects in order to model the manipulator support, as well as we took a real photo of the clamp and integrated at the human-machine interface level. Figure 1 shows the handling station in reset mode. The manipulator is in this initial condition. Figure 2 shows the handling station in operating mode. Now that if the part is present at the station, the manipulator moves down to pick up the part, then moves up to its initial position. Figure 1 shows the handling station in start mode, with the manipulator at the top in front of the conveyor. Figure 2 shows the handling station in start mode, with the manipulator at the bottom and the gripper open to place the workpiece on the pallets. This figure represents the manipulation station in stop mode. Interpretation of results. From the simulation performed for each station, it was found that the WinSys flexible software supervision system follows exactly the actual operation of each station of the MPS 500 system. Also, the human-machine interface performed greatly simplify the understanding of the operation and allow to conclude the main role of each station. This human-machine interface allows to visualize the models obtained in simulation mode and allow the operator to have an immediate vision of the evolution of the MPS 500 process over time by analyzing the sequence of operating states. For perspectives, we want the developing of the rail SCADA control and monitoring system for all the FIS2 MPS industrial system and securing the network part of SCADA. Conclusion. The current and future modern industrial systems are very complex and contain millions of parameters that must be acquired, monitored, supervised, controlled, and managed in real time. For this, SCADA system for supervision, control, and data acquisition are essential. Our work consists of studying, modeling, programming, and developing human-machine interface in order to supervise in real time the parts of the FIS2 MPS 500 system. For this, we use several computer tools, including the schematic Step 7 modeling software for programming, Siemens Programmable Logic Controller, and the schematic WinSys flexible software for developing human-machine interface. The results obtained and presented in the form of figures, tables, and curves with interpretation. So SCADA is a point of interaction between the operator and decision support algorithms. Thank you for your kind attention.